Uh, Thank you, Dr. Velmurugan sir, and Dr. Gopi sir for introducing me. And also, uh, I also thank Sudhantra Vanitha ma'am for introducing me. And then, good morning, everybody. We'll be having a very beautiful session today on interdisciplinary engineering design, product design. Okay, so uh, we'll be starting now. I'll be sharing my screen right now, and we'll start the session directly. We don't have to waste after this. Yeah, one second. I hope I'm audible to everybody, right? Yeah, okay. Is the screen visible to everybody? I hope. Yeah. So this one, it is on multidisciplinary collaboration in engineering product design. So we have to deal about the product development life cycle and how disciplines in engineering is going to be collaborated when product design is that is development of product is happening. It is mostly for the people of circuit branches, that is for electrical engineers, electronics engineers, and then the computer science engineers. It will be relevant. Okay, so we'll start with the what is that we start when we go for product development. So first thing is we have to have a flow of how the product has to work, and we'll be going for the requirement analysis, and then step by step it works. um, One second, I'll make it as a slideshow. Fine. Yeah. So when we are going to develop a product, it will be coming from the management, the people, those who are in the management of the company. Maybe there'll be a techno managers or purely MBA managers. Techno managers means like how I am doing. Actually, I'm a MTech graduate, but I am able to manage a company. So this is techno managing. So the product development process has two things. The product management will be there, and then the engineering aspect of the product will be there. So what the product management does is we actually go to people, those who want the product, get to know about what is needed for them, what is the scenario they want to use, maybe whether it is in a weather condition, also whether it is in a hot area or in the cold area. So all those things we are going to check it out. So who is going to use it, whether it is indoor or outdoor, whether it has to be air cooled, water cooled, oil cooled, many things. It comes in this segment. When I'm talking about market segment, whether it is for business or it is for customers, whether it is for students, that we have to finalize here. That is what I'm telling you. Who is going to use the product, and then why should they use it, whether it is really useful for them, that we have to finalize the scenarios. We have to finalize whether it is really useful for them. So we don't have to give a sweater to people in Rajasthan, right? So that is why. Okay, so why is we have to find out whether it is really useful to the people or not, and then what we have to do in order to get that requirement completed. So this is engineering aspects. So here is where our engineering colleges are training people to get these engineering aspects cleared for the companies. So here features, what do you mean by features in a mobile? For example, how much RAM must be there, how much ROM must be there, and then whether it has a Bluetooth, it has a Wi-Fi, what camera we are going to use, and then gyro and accelerometer, what all is needed on the mobile, GPS. All those things are features. Okay. And infrastructure also, that is in order to develop that mobile, how much infrastructure we have to have, what PCB designer, and how the soldering has to be done. All those things, it comes in infrastructure. And when you're going for technology, uh, which technology, whether we have to introduce AI also inside the mobile software, what is needed for the OS. You know that AI is used in Alexa and other Google, right? So this one, it is the technology. And then user experience, how the user experience, whether it is a capacitive touch, resistive touch, and which hertz the it has to move, 160 hertz, 120 hertz, when you take it mobile, right? How, in what speed it has to move the screen when you touch it. that is 160 hertz, sorry, 120 and 60 hertz is there. So those user experience, if a user is experiencing it, how he feels, that is called user experience. That is what is okay. And how we are going to do what, according to the design specification, what all we have to buy, how we are going to assemble, how we are going to interface it and implement it, test it, verify it, and we have to go to the standards. There are multiple standards. EMI standards is there. We have to pass that standard. Then only a product can come into the market. Fine. So these are the things we are going to detailedly see in our stuffs actually in this PPT. Okay, next we'll start with the flow, how this product development happens. First thing is developing a concept. For example, if I want a robot to be developed which can answer automatically to the people, like the bots, that we can develop using what has to be used in the development, that we have to create when you are creating the concept itself. And then we are going for the development of it. And in prototype is which will be done inside the campus. It will not go out of the campus. First the prototype will be developed, we will be testing it whether our bot is working fine. When I give a input in a particular language, maybe it will be working for only English, so whether we have to improve for other languages also. Everything we have to create in this prototype. And then design for manufacturing is different. See, prototype is different, which will be having the components of which is available directly from the market. We'll be roughly soldering it. All those things will be there in this prototype. But when it comes to the design, right, for manufacturing, it has to be compact, it has to be temperature resistant, it has to be water resistant. These kind of things will come when you are going for design for manufacturing. And then design for assembly. So what when I'm doing the assembly, whether it is ergonomically easy for making the assembly, all those things we have to make it. Because if a screw is there, if somebody is not able to bring his hand to tighten the screw, right, then it is not useful even if you manufacture, right. So that's why for assembly also there will be a particular way of designing it. And maintenance and technical support. So after the product goes out, some of the products will be annual maintenance will be there. And if there is any defects in the product, the technical support has to be given to the product. So this is how product development cycle will be. Then okay. So the thing is what in concept phase we do. So first thing is market survey and study. Already we have talked about it. The second thing is the main thing. Most of us we never do it. Brainstorming and requirement identification. See, when you are talking about brainstorming, you have to talk with people, those who are using it, and you have to talk to the people, those who are developing it. And idea creation also, you have to talk a lot of people, so that brainstorming happens. See, what happens is suddenly you will be thinking of developing a particular product which may be already there in the market. See, I was planning to develop a bamboo based water can. Okay, so I thought it was innovative. I thought I am the one, I am going to do it as a first person. But a person from I think it was in Assam or Arunachal Pradesh, I don't know. That guy had worked on that for 17 years, and he had created a bamboo based water can. Okay, so on with a cap, steel cap. You can search, if you search in the Google, you'll be getting it. I actually started this idea only before 2 years, but that guy, he has worked for 17 years. So this brainstorming, what it will do, people those who know about multiple products, right, they will be able to tell you, no, this is already there, or what improvement can be done, can be told. So this is what is brainstorming thing. Okay, I'm also telling about my personal experience. I also had the experience of getting going back. Okay, so this brainstorming is very much important. And then analysis of feasibility of design. See, sometimes what you think is, once I was teaching somewhere in Trichy. I was talking to a student. At that time, the power transfer through air was not there. That is, the wireless power transfer. Now the Samsung is giving, the Samsung and multiple companies are giving wireless power transfer. At that time, that guy was telling, I want to send power through air itself. But what I told him, it is not possible at that time, because the feasibility was not there. That is what is feasibility. Now the feasibility is there for wireless power transfer. Even high power also in New Zealand they have tested that high power transfer can be done. It is a inductive induction, mutual induction. Using mutual induction, it can be done, right? And then before going to before going to the product design, proof of concept has to develop. See, proof of concept is that that is necessary for copyrights, patents, and then before going for product launch, right? Proof of concept must be there. That means that if you have developed a particular product for a particular purpose, whether it is working for that many days. See, for for example, LED lights, right? It has to work for 25,000 hours or something like that. They test for that many hours, whether it works or not. So these are the things that we have to check out, and whether there is a depreciation in the power value, or when you are having a VLSI design, whether the IC working of the IC is continuous or not, those kind of the glitches is available or not. So all those things we have to check using this proof of concept. And you know that before getting that to be a product, you have to go for simulation and check all the things, whether it is working or not, before you go for developing it. And then see, if you're developing a product people can't buy, see, if you think that is new, but somebody can't buy, then it is not useful at all, right? So you have to make sure that it must be, if you're developing a landline phone for 16,000 rupees right now, mobiles are already there, right? So that is not useful. So that kind of cost analysis you have to do before a product is outside. Okay, and then this is the user interface. UX is user interface. When a particular user is using a application or anything like that, it should be very easy for him to use it. So it must be a click or a button switch or something like that, which will be very useful for him to access it. Okay, so this is the concept phase. And then um, right now what I'm talking about is for only for the circuit branches. So when we are talking about circuit branch, you know that we'll be having ICs, right? That is integrated circuits. That is what we use in day-to-day life. Even if you are an electrical engineer, if you have seen MOSFETs, thyristors, all those are ICs, right? And even diodes are all ICs, because you have a PNP layer, P layer, whatever, you know that, right? So those are ICs. So using those ICs, we are going to apply some application. MOSFET means it can be a DC-DC converter, inverter. If you're having a embedded ICs like Raspberry Pi, you'll be using ARM processor in that. So these ICs are the major thing for all the circuit branches, like ECE, electrical, and then the computer science. All will be involved these things. So uh, when it comes to electronics engineer, this particular ASIC design is a prime thing. So you can see that this flow, I'll just tell you what happens in the flow of IC design or VLSI. So product specification will be taken, whether you will be forecasting whether 5G has to be used in that or not, and you have to check whether which package you are going to use, whether it is on SMD. SMD means which will be on the board itself. You will be soldering. Dip package will be there, which will go inside the uh, PCB, and you'll be soldering on the other side. So these packages you have to check out. The companies like CERN, NASA, CG Corel, all are working on VLSI design. Okay, and these things you can search in the net about these companies. Then architecture. So this usually is done by people those who are doctorates or MTech, those who have completed the MTech. They develop this ASIC design. First thing is you'll how the blocks has to be connected in order to get a particular output. So for example, if I'm planning for multiplication or addition, how the gates has to be connected, and NAND or gates, how it has to be connected, and how the output has to happen, and ALUs. If I'm planning a complete microcontroller, if I'm planning a complete DSP processor, the whole architecture you'll be developing, that is done by those who are experts, those who have already worked on that in for around 20-30 years. They can do this architecture. Maybe if you are smart enough, 5-6 years is enough to reach that age, that is that particular place. Okay, and then logic design, and it is also called as front end design, where we write Verilog VHDL codes to connect the gates in such a way that a particular work happens. Maybe it is multiplication, addition, ALU, microcontroller. The whole microcontroller you can design in the front end design. And then routing, all those things, physical design. It is like how the transistor level connections are happening, that you do it in the physical design. And routing also, how it is connected without the glitches. Clock tree synthesis, I think you know about the clock tree synthesis. There must not be a glitch. Two process or two instruction cycle should not at once, it should not work. There should not be any glitch. If there is a pipelining concept, whether the pipeline is properly working, all those things we have to uh, work on this physical design. And then the tape out is that is a fabrication. After you connect all the transistors in a particular design, then you'll go for the fabrication. You'll tell people to make the IC out of it. Okay, so that is the tape out. Okay, so it is done by Samsung, Texas Instruments, TMSC. You can search TMSC in Google and you'll get that. Okay, so how the chip it has to work, all those things, it will come in the verification stage. That is here the verification in software also will be there, and then after you create the IC, there also you will be verifying whether it is working properly or not. And if there is any problem, it will be going back. Most probably fabrication, before going to fabrication, everything will be dealt, because this is a costly process. So most probably until the physical design itself, everything will be finalized. So I want to just tell about what is a ASIC and what is a FPGA. Okay, so application specific integrated circuit. And what is FPGA? I think first year students, maybe they'll not know. Third year students, any one of you, can you? Friend, philosopher, guide and advisor, is it? Yeah, it is field. Yeah, field programmable gate array. Okay, so this is also friend, philosopher, guide and advisor. You can also remember that this is field programmable gate array. Okay, So this one this means that you are able to connect gates in a array in such a way that it works for a particular cause. Okay, so now whenever you are talking about FPGA, you have to think about the idli batter. uh, I think you know about what is a idli batter. Everybody would have had it. That is, this is the same thing. We use it for idli and dosa both, right? So here, this gate array, that is the floor. Okay, that means that you use the gates in the transistor level, and you connect it in such a way that either you will get a idli or you can get a dosa. Here I'm talking about either you can get a microprocessor also, you can get a DSP also from the FPGA. ASIC is this idli only or dosa? uh, See, FPGA is nothing but the floor, which is common. Application specific, it is ASIC. Okay, so FPGA, you, that is a floor. From that you create ASIC. So from the floor you create idli and dosa. So this you have to always remember. So this is for the product designers. ASIC is the one we always design, and we actually give it to the ma- market. ASIC is the one we actually give it. Fine. So this is about FPGA and ASIC. It is just to remember how, for the first year students, I think it will be more useful if you remember FPGA as the idli batter and ASIC as the idli and dosa. Fine. So now, what is that engineers do here? Okay, engineers in this process, how they are involved. So these are the jobs that people get while they are in the VLSI design platform. See, architecture, already I've told you, architect, he'll be a PhD or MTech usually, and then FPGA programmer or the front end programmer. That's what they tell, front end programmer. These places the BE engineers will go into. Verification engineers in order to verify the routing, and then analog design engineers, those who develop ADCs and DACs, which will involve both the analog portion and the digital portion. Here analog digital design engineers will be there. And when it comes to fabrication, where the ICs are physically made by using the NPN layer, that it is IC design engineer. Also they are told as yield integration engineer. This one, it is not usually used in India, this term. It is used in other countries. Okay, so these are the uh, these are the engineers, those who are involved in developing the ICs. The basic thing for all the circuit engineers is you should have a IC. So these engineers in this process, or these are the engineers. Mostly it will be from the electronics background. ECE students will be involved in this. I don't think any electrical engineer will be involved in this. Most probably. So this is the thing. Fine. Then this will be the this is a example of a 30 nanometer technology IC, which has the pinouts. You can see these are the pinouts, and here the transistor level circuits are connected. Transistor gate level circuits are connected, and pinouts will be there. I think you would have seen in many of the um, boards. If you see on a CPU, you will find ICs like this. The QFP package it is. Okay, fine. Next thing is we are talking about embedded system. See, actually, the thing is these ICs. These are hardware, right? If there is a RAM on it and ROM on it, why is RAM and ROM used? Storing and calculation also is involved, right? So when hardware is there, software also has to be there in order to make it think. Okay, so why I'm showing this samosa? Can anybody guess? I think most of you know about this samosa, right? Yeah. My favorite is the aloo one. I mean the potato. Anybody? Any guesses? Yeah, yeah. So what do you? How do you justify it? Okay. Yeah. That is right. That is a software, right? That is the essence of the product, right? So the essence of the product is the masala inside it. That is the brain. Uh, that is some people tell. உனக்கு மசாலா தலையில மசாலா இல்ல that's that will tell, right? Usually that means that the brain that is actually working for the product. Okay, and then which is holding that software is the hardware. Usually rom and ram, it is holding it and it executes it. So this is a complete embedded product, right? So whenever you think about embedded, it should have both the masala, which is the software, and the floor that is covering it, that is the hardware. So that's how I've taken samosa as a example. Fine. I think don't think I'm a complete foodie, but these are the examples I could take. Okay. Yeah. Here, yeah. So hardware design and the software design. Okay. So schematic capture. First thing is you have to create a schematic of the whole hardware. See, when schematic is not the IC design, it is the accessories that you have to connect for the IC. I think you'd be knowing about the power supply, and you will also know about what all interfacing has to be done. Whether if it is analog to digital converter is there on the IC, then you have to allow some pins for the analog input to be given to the IC. So those things, it will be developed by schematic capture. So you have to just create a schematic first on paper, and then you have to also check for the part selection, which is like if you are taking a microcontroller or microprocessor or any other ICs. For that, you have to be giving a supply, and you know what are the pins that is there, and whether what pins for this particular application I need. That is the system design engineer's work. See, here I have told system design engineer who does the things for hardware design and the software design. He'll decide everything on this. Okay, so schematic, first the thing is I have to draw. See, I think you would have used 7805 or 78, that it is just a regulator, 7805 regulator. So you know that in that there are three pins. One is input pin, one is output pin, and then one it is a ground pin. So these three pins, if I have to use it on a board, for that I have to create that hole for the dip package. So that schematic is taken care. Okay, and then part selection, whether which particular uh, company's IC I have to use, that is part selection. 7805 may be given by some multiple peoples. Okay, so that part selection I have to do, and then PCB design and board layout you have to create, right? So whenever you are developing the board selection, then first the thing is you have to create the layout of it, and then the assembling will happen. And then after this assembling is done, if it is a embedded board, then you have to go for the software design also. Maybe if it is a, driver development, or if it is a autos, or it is a just dumping the program on the IC. those things you develop here, and then you develop the coding, and then you actually integrate the multiple reusable softwares, that is the functions that was already there, like serial programming. For that function will be there, read, write, all those things are components that are already available. And then you'll be testing whether the software is working on this hardware. This is the hardware, on that software you are dumping it and checking it. So this is about the embedded engineer, and the designation will be usually system design engineer. Okay. And then, yeah, here the engineers who are involved in this step is, the first is I told about the system design engineer. He will be designing the whole product, and then software engineer will develop the coding, C programming, keel compiler programming, like that, and Python programming. Those kind of things he'll be developing for this particular product, if it is an embedded product. And hardware engineer, who makes the soldering, and also sometimes he'll test, not only soldering, he'll test also. Usually hardware engineer will be also a testing engineer. If the company is really big, then hardware engineer will be separate and testing engineer will be separate, and these two things will come. And also people will also check for the size of the board. All those things has to be checked, and if the size of the board is bigger, then it will go back to design engineer, like that it happens. And then field application engineers are, in many companies, those who are IC suppliers. If a company is supplying IC, they'll be, if a manufacturer is buying a IC from the company, he doesn't actually have the whole team of design engineer, software engineer, hardware and testing engineer. He will not have it. He only want to produce the product. He doesn't want to develop it from the scratch. So IC suppliers, right, they will have field application engineers. They will work all this work, like design, software, hardware and testing, for that particular product, and they give a model design to the company, those who are manufacturing, and then it goes for manufacturing. So this field application engineers will be available in many of the suppliers, or if you are taking multiple suppliers, yeah, a dealer will be there who will be having this field application engineers. I think you can search for Arrow Electronics, Abnet Electronics. These are the people, those who are hiring people, like field application engineers. Fine. Then, now there is a trend of AI on VLSI. Like you can create a chip which is intelligent. That is, instead of writing a software code through gate itself, the intelligence they are producing. The thing is, that is, if the code is going to run on a RAM or the ROM, again it will be going to connect a gate in a particular way. So that connections of the gates, if it is on the software, directly they are creating on the hardware itself, so that a particular way of thinking can be developed on the IC itself. So this has a flow like this. One second. See, there is a training. Uh, Yeah, there are two portions: training portion and the testing portion. The top one is the training portion, bottom is the testing portion. So the thing is, whenever you want to train, I'll give you an example of how training is done. Anybody have pets in your home? Pets, any dogs or cats? Anybody? Yeah, okay, not a problem. See, if you have a pet in your home, you just try this. How the training, the example of training is dog and bell rule. Okay, so for the thing is, you will be feeding that dog or a cat at a particular time or with a particular vessel, right? So you take that vessel and just keep it before giving the uh, food to the pet. It will actually have a salivation, like dogs and all. No, it will be salivating. Uh, எச்சி ஊறுறது. That is what I am telling you. Salivation. Okay. These dogs, right? Initially, they will not find out that bell is rung before they are fed. Okay, so what you do before giving the food to the dog, you just ring a bell and then you feed them. But usually, the thing is, whenever you take that vessel for feeding it, that during that time itself, it will be salivating. But slowly, what happens? Once the bell is rung, it will have the training that, oh, they are giving us a food after a bell is rung. Okay, so slowly what happens is, in a month's time, it will train itself to salivate on the ring of the bell itself. Not it will not wait for the vessel to come. Okay, so that is called training. So you have to have lot of input and output pairs for training it. So here, this is data set is having both input and output. You will give it to the brain. You just take this whole thing as a brain, and you are giving it to the brain and telling the brain that this is the output. Okay, you have to salivate. That's what we are telling the dog, right? So yeah, that input and output pair will be given, and it will get trained, and you will have a training model which will be giving us the output. Okay, so the trained, that training you are trying to do it on a VLSI IC. Okay, so training and testing will be happening on the online. That's what they tell it as, online. Fine. Okay, so the engineers, those who are involved in that is the data scientist, the VLSI engineers. These are the people, those who are involved, because the concept of learning is developed by the data scientist, and then that learning concept which you want to build on a IC, that is developed by the VLSI engineers. Fine. Okay. So other applications where these particular AI VLSI can be implemented are image processing algorithms, video processing algorithms, audio processing, automation, control, PLC, and power electronics. These are the many applications the VLSI ICs can be used. Directly, you can develop a IC for image processing or any of these. You can directly make a IC out of it. Nowadays, power electronics, right? It has pulse generators and the MOSFETs on a single IC. We don't have to create a pulse separately and give it to the MOSFET. In on the single IC itself, you are having both the pulse generators and the MOSFETs. Not nowadays; it is long before it has started. Okay, so these are the applications. Even machine learning algorithms you can implement. That is, you can create a IC for ANN or anything like that. Okay, so these things, again, this in most of this, the electronics engineers, EC background engineers, they can get involved. Fine. And then when it comes to power electronics, some of the electrical engineers also will get into involved. Fine. So hardware development, I have already told you, both software and hardware will be there. In hardware, I have told you the schematic capture. Before schematic capture, you have to create the simulation and check whether the schematic is working, and then you have to go for the same component selection. And lifetime analysis is one of the things. See, when you are taking a product, uh, that if you are giving it over a product, a particular IC, it has to work for at least some 10 years. When it comes to defense, it will be more than that. Maybe around 20 years they will give the lifetime analysis. If you are using the same IC or the similar IC in a defense platform, that is when it comes to army or Navy or Air Force, these ICs will be having a higher lifetime. But when you are using it for our domestic purpose, then it will be for only 20 years like that. The IC will be warranty. The warranty of the IC will be that much. Then the PCB will be taken and fabrication. PCB design will be making and fabricating on the thing. And then there are multiple compliances that you have to do. That is standards you have to maintain. Environmental standards. That is, it has to withstand a particular level of what is that temperature, from negative temperature to the very high temperature. It has to if you are going with that IC to maybe if you're going for Kashmir or Rajasthan, which is having a opposite temperature levels, so these environmental standards has to be maintained. And IEC radiation standards, whenever you are going for space or anything like that, right? During that time, radiation standards also will be useful. And other EEC, there are multiple standards. Lead free, you have to make sure that it is lead free. That is, the soldering must be lead free. And then CE standards are there, and EMI standards are there. And that is, you should not have the electromagnetic interference on the ICs. So these kind of things you have to make sure that that is whenever you do the hardware, these kind of things has to be taken care. And then software development, you know that usually it will be C, C++, RT Linux, Python, VxWorks. These are things we use it for the embedded hardware things. Okay, and then code generation according to project requirement. See, this is for a particular this is the standard. IEC standards are there for uh, for a particular mission. If you are using it, so these kind of standards you have to maintain. Okay, so you can search on the Google for these things. Okay, software development. Okay, and then major thing for all the ICs, right? It has to be powered, right? It has to be given a power. Either it is a 5 volt, 3.3 volt, or now it is 1.8 volt. Processing also has started. Slowly, I think it will be having zero point 0.8. Also, the the mm, IC's nanometer thing is there. No, if it is even getting down, right, then voltage will get reduced. So when it was in the microcontrollers, we were using 5 volt and 3.3. When nanometer technology came, 3.3 and 1.8 has started. If you go beyond that, they are telling that even 1 volt or zero point 0.8 volt processing will happen. So the process, but anyway, we have to have a power supply for that. Any ICs or anything like that, you have to have a power supply. So we have to make sure that there is a power supply which is compatible for that IC or the PCB design. See, when you take a CPU, you have a SMPS in that, which will be creating multiple voltages, 12 volt, 5 volt, according to which IC it is supplying. It creates multiple outputs. 12 volt will be there sometime. Some places it will be 5 volt. So that is developed by the power supply design engineers. Okay, so this is one of the small power supply board. Actually, it has a output here. Here AC input is given, and here DC output is taken. So like that, they have created a 12 volt DC supply this way. It may be a buck converter or boost converter. This is the name given to the converters which increases the voltage or decreases the voltage, like that. The names are given, that you can, when you learn power electronics, you'll get to know that. Fine, right? This is power supply design. Okay, so what is a requirement that they take it from for designing a power supply? What is the input voltage? That is voltage range. There is a thing called universal voltage range. So when you talk about universal voltage range, what is that? Can you tell me what is the voltage range in America and what is the voltage range in India, there is supply voltage. Can you tell anybody of you? In America, what is the AC voltage coming out to the domestic usage? Any of you? In India, anybody? You know that it is 230 volt, right? Okay. So, see, actually, in India and many other countries, it will be 230 volt or 240 volt, and in America, it is around 110 volt. Okay, so when this input is asked, if they are telling it is a universal input, then it has to be from 85 volt, that is from 110 some 5 percentage less, and then until 270 volt, from 240 some 5 to 10% higher. That range it has to be working. Okay, from 85 volt to 270 volt is the input voltage range, and output voltage, it can be a 5 volt DC or 12 volt DC. And then what accuracy it must be, 90% accuracy, that is according to the drop of the ICs, and also the drop that is happening because of the circuit components. So those things they will be asking as a developer, that is if a power product is there, no, if they are developing it, they will ask these things: input voltage range, output voltage value. So AC input and DC output. Sometimes AC input, AC output itself. Sometimes DC input, DC output itself. Like that, different converters are there. Okay, so those converters are called power supplies. Okay, then load. What is the to which load you are giving? Whether it is for a LED load, or you are giving it to a fan, or like that, you are giving it to a motor. Those things you want to know in order to know what current it has to give out. If it is a LED, if it is a wattage 18 watt or 20 watt, it is low current. If it is a motor which is of 100 maybe 5 HP, 6 HP, like that, then more current. So for that, the mm, output will be AC or DC, and for that, how much current is needed, that is the load requirement, that is called required current. And then efficiency and standby power. So how much efficient it must be, that is the loss that is involved in that must be less, so that the efficiency is high. And standby power is whether I have to have another battery or something that can supply when there is a loss of power. Okay, so that kind of thing they'll be implementing. And I told you about Rajasthan's condition and the Kashmir's condition. Rajasthan is a complete desert, maximum temperature, and Kashmir is a you know that it is completely cold, right? So then there it is a minimum temperature, and any cooling required. See, if it is high temperature, right, then we need to cool the ICs. If not, ICs will burn. So in order to avoid that, we'll have that is heat sinks, and also you'll be having air cooling fans. I think you know, in each of the CPUs you can find fans in the SMPS, because you need to cool it, because it should not be hot. Okay, size. So how much size it must be? So ICs and all, they are making it nanometer technology, because in order to reduce the size, mobiles have reduced its size because the technologies has reduced the size of the ICs, and also the needed power supply also will get reduced, right? That's the thing. And whether under voltage, over voltage protection, or overheating protection has to be done or not, that has to be taken care. So that is they'll be create having a fuse, or they will have a relays in order to remove if there is a higher voltage coming in. If it is under voltage, it has to indicate that there is an under voltage input. In UPS you will find this. If there is a under voltage, it will not charge, so that it will show it it is under voltage. And over voltage, if it is there, it will trip. Okay, so like that. and overheating if it is there, automatically some of the systems, right, if it is highly heated, it will automatically shut down. So these kind of things we need to as or the people will tell us these are things we needed. And special environment operant conditions, whether it is on the vehicle or whether it is on space. When you are going for space, right, again I told you about the IEC radiation, right? Radiations will be high when you go for space, so during that time also you need a EMI testing done properly so that it can be sent. And communications, whether it is RF communication, Bluetooth or Zigbee or OFDM. There are multiple things that we'll be using for communication. Which particular communication you need? 4G, LTE, 5G, all those things will come here. And RF technology also. Okay, radio frequency technology and other factors you have to ask them. Okay, so if the see if there is a it is used for RF for communication, it there is a chance of EMI introduced on the power supply also. So in order to have that removed, right, they'll use filters in order to avoid EMIs from other sources, or they have a particular design for removing the EMI, right? Like that they can try. So required certification or standard, that's what I told you. CE certification, let free. There are multiple certificates that will be there that you have to use it. And then cost factors also. There you have to which IC to buy. If they are telling 1,000 rupees for that, what is the IC I have to buy? If they are telling the 5,000 rupees for that, what is the IC? So that cost factors also will be the specifications. Fine. And then in this, what are the who are the engineers they are involved? It will in these power electronics based engineers, most of them will be electrical engineers, and sometimes electronics engineers are also involved in this. So this the designations are field application engineers, PCB design engineers, hardware engineers, and testing design engineers. Fine. So these are the engineers who will be involved in developing the power supply of this. Fine. Okay. Next thing is, yeah, and then here the software engineers and also the EC engineers also will get involved when it comes to human machine interface. See, whenever you see mobile, right, you have all the UIs, right, on the mobile. So to send a mail or you in order to open WhatsApp, everything you have UIs. So in order to send a message, that is a UI, user interface. And then if you are having a PLC, CNC machines, when you're if you talk to your mechanical friends, right, they'll be having CNC machines, computer numerical control. That is how many, if they want to cut a particular piece in a particular shape, right, they will just give it in the user interface. Automatically it will cut in a square shape in this particular dimension and cut that into a piece and give it. That is human machine interface. It is done by the software engineers or even the EC engineers. They work on this. And you have to make sure that it is clean and responsive. See, if you press a switch after 10 seconds, if it is responding, no, then that is not useful. And it should be clean, it should not be cluttered. Many things it should not be available on the box. You know, you don't need the temperature, all those things, because it is having already safety measures are taken care. You don't need the temperature to be displaying on the UI. You just need on off how much time it has to be, like that you have to make it very clean here. Okay. And then semiotics is nothing but the science. See, when you are talking about science, right, I think here, this, if you see this, you can see that it is a camera, right? Here if you see this, it is telling that is recording, right? And then this is settings. So these are the semiotics, that is nothing but the science. Okay, that also has to be there on for the product, for the user experience, so that he'll be able to easily find out what it is. Okay, so that semiotics, it is called semiotics. And then aesthetics. See, when you are talking about aesthetics, the um, shape and design of the product, whether it is curvy. When you see a mobile, it should not be rough to handle. If you have a water bottle, it should not be rough to handle. It should be very soft. It should have a particular aesthetics. It should look good. That is what is called aesthetics. And then colors. Colors also, it should not be very dull or something like that. That is, it should look very attractive. Okay, so physiological response must be good on that color. Okay, so this is the user experience. It should happen on a product. Then see you for that to happen, for this particular semiotics, sorry, I mean the aesthetics and the color, right? Then your friends from mechanical engineers will be used here. See, conceptual and detailed design of mechanics, like how it, see, this is a box. See, they have made that is option for screw, right? The box must be very small, so the for screw itself they have made it a small portion, which will be avoiding the space. If the screw is going beyond the box, it is not beyond the box. Within the box itself they are screwing also. So this kind of efficient design has to be done by the mechanical engineers in order to make a box. If I want a mobile to be having a cover, right, it should be proper and it should be looking very good. Okay, and they actually develop a 3D printing first. That is what is called 3D prototype. After giving it to a CAD software, that is computer aided design, you design this mechanically, and if you are having a 3D design, you can make it and see using a prototype, and then you can go for the manufacturing. So 3D will be, if you are printing completely all the products using 3D, it will be costly. Only for prototyping, you can use 3D prototype. When you are going for manufacturing, you have to go for other techniques, the casting, all those techniques, that is all involved. Okay. So this is called CAD, that is computer aided design. That is only for covering the product that the people from electrical, electronics, and computer science make it. So it has to be covered. So mechanical engineers will work for that. So here, the engineers, those who are working on the product, covering or holding it or whatever it is, that is CAD engineers. I think you'll be knowing about softwares like ANSYS, ProE. There are multiple softwares. I think a lot of institutions are there. They train ProE and ANSYS and other stuffs, right? So CAD engineers actually they design it in a 3D way. Okay, and then material engineer is there. Maybe it is not the exact word, but what they do is, to that 3D design they'll apply the material characteristics. See, you can, once the 3D design is done, it can be plastic also. At the same 3D design, you can use it as iron or aluminum or any other material, right? So you can apply that plastics analysis on that material and check that guy is a material engineer or analysis engineer, I can tell it as, or finite element analysis, something like that. They apply it in order to know what is the stress. If somebody is standing on the mobile, whether the mobile is will break or not. If the mobile is thrown on a wall, whether it will break or not. So that stress applied on the cover of the mobile, no, that they are going to check. That is a mechanical engineers do. And then fabricating engineers actually, whether you are going to cast it or whether you are going to use a what is that CNC machines for that. So those come under fabricating engineers. And you can also tell them these fabricating engineers also include these CNC engineers. Okay, CNC is computer numerical control engineers. Those, they will be having a precision cutting machines. If you want to cut a particular wood or steel or anything in a particular shape, You have to just give a input in the HMI, that is human machine interface. It cuts and give you a particular shape. So there are two ways of creating that. One is additive and subtractive. See, additive is 3D design. And that is the if you nothing will be there, you will be creating a shape, that is additive. But in subtractive, you will have a square shape. From that, you can create a sculpture. Okay, that is what is subtractive. So 3D is additive and CNC is subtractive. This 3D is only for prototyping you can use. CNC, it is for mass production. You will be using it. Fine. So these are the things that is this is the interdisciplinary product design flow. The engineers involved in each of these steps, I have just given you an idea. Mm, and actually these videos and all will be uploading on the YouTube also. You can I'll be also sharing the YouTube link to you. This is our channel. You can also check out other technical videos that is based on different machine learning algorithms, power electronics, this many other things are there. You can just check in this YouTube channel also. I'll be sharing this link also. So that is all for today about the product design life cycle, where engineers from electronics, electrical, computer science and mechanical all have to work together in order to get a product done. So if electrical engineer is not there, power will not be there for the IC. And if the electronics engineer is not there, there is no IC itself. Another thing. And then if mechanical engineer is not there, there is no cover for that for the whole product. Okay, so and then logic, you can either get a help of the computer science engineer, or EC engineers also can develop that, right? So this is what the interdisciplinary uh, product life cycle is about. So this is how you actually go for interdisciplinary product. That is, product is always interdisciplinary. You have to develop it by the help of different engineers from different departments. Okay, so this is all about the seminar. If you got any queries or any doubts on this, you can ask me now. Thank you. Yeah, if you've got any doubts, you can ask me. Yeah, thank you, sir. Thank you. Yeah. Thank you, sir. Velkumar sir and Gopi sir. I also. Thank you, sir. Thank you. Sure, sir. We'll do that, sir. 100%, sir. Sure, sir. That will be done. That we can do it. Yes, sir. Yes, sir. Sure, sir. That will be done. That will be done. That's what. I have also shared the YouTube link where many technical videos we are uploading. So this is the I've shared in the chat. If people are interested, they can subscribe to that channel, and they can also see multiple concepts that we are. And this particular video also we are going to upload in the YouTube channel, the same channel, and they can watch in the YouTube itself. This again, if they have got any doubts, they can comment on that channel itself. Yes, sir. Yeah, thank you, sir. Thank you. Uh, Thank you, sir. Thank you. Thank you, sir. Thank you.